In this video, we will discuss polynomials. This is not so much a topic from linear algebra, but some skills that you will need when we go into eigenvectors and eigenvalues. And because we're going to be looking at characteristic equations with complex coefficients, some of this material may be new to you. This is the overview slide, which we'll spend about 5 minutes going over before we go over each topic and in more detail. And because this chapter is mostly about giving you tools to use in subsequent chapters, I will be emphasizing how to solve certain problems as opposed to the real understanding of why things work, and I will state many theorems without proof. We will start this video by reviewing complex numbers. In general, we'll denote complex numbers with the letter Z, and we'll have Z equals A plus IB, where A and B are real numbers. Then this A is called the real part, and B, which is multiplied by I, will be the imaginary part. We will designate that as A equals RE for real part of Z, and B equals IM for imaginary part of Z. We'll discuss the complex conjugate and also define the absolute value of a complex numbers. We'll do a number of properties of complex numbers, which were too numerous to mention in this overview slide, but we will go over a few properties. We will get into the main topic of our video, which are polynomials, and polynomials over a field F. We define that as P of Z is equal to A0 plus A1Z plus A2Z squared up to AMZM, where the A0, A1, A2 up to AM, they're all elements of our field F, and our Z is also an element of our field F. So the statement must be true for any Z in the field. Many of the things we'll go over in this video is familiar to you because you're used to polynomials from algebra from middle school, except that now we have the possibility that the field is going to be over the complex numbers. So there are differences between handling polynomials over a complex field and polynomials over a real field. So we'll cover the complex field first and then treat the real field as a special case. Perhaps the most important thing we will be doing is factorizations of polynomials, because that's what we're going to use when we talk about eigenvectors, eigenvalues. We'll need to factor the characteristic equation. So first we start with factorizations of polynomials over C. That's complex numbers for coefficients and also complex variables Z. We have the fundamental theorem of algebra. Every non-constant polynomial with complex coefficients has a zero. So as long as our field is the complex number, we are going to find a zero. To factor the polynomial over C, we're going to use the synthetic division here, which we will review in the main part of our video. We will then move to looking at factorizations of polynomials over R, where we have real coefficients. A polynomial with real coefficients may have no real zeros. So if we're constrained to only the real numbers, and not the imaginary numbers, we may have no real zeros. We have this theorem here that polynomials with real coefficients have zeros in pairs. That is, suppose P in the space of polynomials over complex numbers with real coefficients, if Z1 is a complex number, if Z1, a complex number, is a zero of P, then so is its complex conjugate. So again, the polynomials with real coefficients have zeros in pairs. If Z1 is a zero, then so is Z bar, or its complex conjugate. We have this theorem of factorizations of a quadratic, which you are probably familiar with from algebra from middle school. Suppose B and C are real numbers, then there is a polynomial factorization of the form x squared plus bx plus c if and only if b squared is greater than or equal to 4c, because this is what in the quadratic formula you use to solve these quadratic equations, this is what goes under the square root. So if you're limited to the real numbers, then the polynomial has a factorization if and only if what under the square root is positive. We have this next theorem, factorization of a polynomial over R. Suppose P is in the space of polynomials over the real numbers, and it's a non-constant polynomial, then P has a unique factorization except for the orders of factors of the form C times x minus x1, x minus x2, x minus xm. These are the real roots. X squared plus b1x plus c1, b2x plus c2 up to x squared plus bmx plus cm. And these quadratics are where our b squared is less than 4c. So it does not satisfy this condition here for another real root. That wraps up our overview, so we're ready to go back and take a closer look at the complex numbers. As I had mentioned in the overview, our complex numbers generally will try to denote them with the letter z, or z1 or z2. So z is equal to a plus bi, where a and b are real numbers, but you can see this b is multiplied by the imaginary number I, so we refer to a as the real part of our complex number z, and b as the imaginary part of our complex number z. We will then define the complex conjugate of z, which we will notate in this book with z bar, is equal to the real part of z minus the imaginary part of z times I. So for z equals a plus ib, the complex conjugate is a minus bi, or ib. And the absolute value of a complex number z, which we will denote with the regular absolute value signs, is equal to the square root of the real part of z squared plus the imaginary part of z squared. And our example here is z equals 3 plus 2i. So the real part of z is 3, and the imaginary part of z is the thing that's multiplied by the I, that is 2. Our complex conjugate then is equal to the real part of z, which is 3, minus this imaginary part, which is 2 times I. So it's 3 minus 2i. Our absolute value of z is equal to the square root over here of the real part squared, that's 3 squared, plus the imaginary part squared, which is 2 squared. So we have the square root of 13 for this example. We have a number of properties of complex numbers. I'm going to state many of them without proof. Some of them are fairly straightforward to prove. The two that I will spend a little bit of time on is property 3 and property 9, but for now let's just list them. First, the sum of z and z complex conjugate of z is equal to z plus z bar, which is equal to 2 times the real part of z. The difference of z and z bar is equal to z minus z bar is equal to 2 times the imaginary part of z times I. The product of z and z bar is going to equal to the absolute value squared. And we have additive and multiplicative property of the complex conjugate, which is the complex conjugate of w plus z equals the complex conjugate of w plus the complex conjugate of z. And the complex conjugate of w times z equals the complex conjugate of w times the complex conjugate of z. We have the conjugate of the conjugate, in other words, z bar bar gives us back z. The real and imaginary parts are bound by the absolute value of z. That is, the absolute value of the real part of z is less than or equal to the absolute value of z, and the absolute value of the imaginary part of z is less than or equal to the absolute value of z. The absolute value of the complex conjugate is equal to the absolute value of z, and the multiplicity of the absolute value, that is, the absolute value of wz, equals the absolute value of w times the absolute value of z. And finally, we have the triangle inequality, which we often use when we're trying to prove or put an upper or lower bound on something, which is the absolute value of w plus z is less than or equal to the absolute value of w plus the absolute value of z. So let's take a quick look at 3 and 9. We'll start with z times its complex conjugate is equal to the absolute value of z squared. So we can multiply z, which is a plus bi, times its complex conjugate, which is a minus bi. So here we have a squared, here we have minus a plus bi, here we have plus a plus bi. So those are going to cancel out. We multiply these two together, we're going to get minus b squared times I squared. Well, I squared is negative, so that gives us back to a positive b squared. So that's a squared plus b squared. We can take the square root of this and then square it and have the same number, but this part here you'll see is exactly equal to the absolute value of z squared. And that's the property here, property number 3. The next property we will talk about is the triangle inequality, property number 9. We're not going to prove it. The proof is in your book, and I'll also state that often it's used in proofs, for example, in proving a maximum or minimum, like a boundary, a maximum boundary or a minimum boundary. But the idea of this triangle inequality is if you have a vector w and you put it tail to head with another vector z, and then you can form the vector that's the sum, you'll get this triangle. And from properties in geometry, the absolute value of w plus z is always going to be less than or equal to the absolute value of w plus the absolute value of z. Our next topic is of polynomials, that is polynomials over a field f. It maps from f to another field f. So we say this is a polynomial in f if there exist coefficients a0, a1 up to am in f, such that p of z, z also comes from f, is equal to a0 plus a1z plus a2z squared up to amzm. We have this theorem that says coefficients of a polynomial are uniquely determined, which is something which is probably natural to you from middle school algebra. But this is a result of the following theorem. If we have a polynomial p of z is equal to a0 plus a1z plus a2z squared up to amzm equals 0, then a0 equals a1 equals up to am equals 0 for where every z and a0, a1 up to am is in f. So in other words, it follows from this theorem because if there were two representations, then we could subtract one representation from the other, and then we could use this theorem to conclude that the two representations must be equal. Next, we have the division algorithm for polynomials. Suppose that p and s are polynomials and s is not equal to 0. Then there exist unique polynomials q and r such that p is equal to sq plus r with degree of r less than the degree of s. I don't know if this will help you, but this is what puts there's an analogy between this division of algorithm for polynomials and the division algorithm for integers, which helps me understand the division algorithm for polynomials. And that division algorithm now for integers says if p and s are non-negative integers with s not equal to 0, then there exist non-negative integers q and r such that p is equal to s times q plus r, where r is less than s. Usually we say s is the quotient and r is the remainder. So in other words, if we have p and s, we can divide p by s, get our quotient q, and we might have a remainder. So that's the same thing here. If p and s are polynomials, we can in effect divide our polynomial p by s, and we'll get our quotient polynomial q plus our remainder polynomial r. And the important thing about the remainder here, for integers, r is less than s. For polynomials, we're going to have the degree of r is less than the degree of s. And so this is what we're going to be using, the division of polynomials. However, the proof of this theorem here is interesting, but it's not constructive. In other words, it doesn't give us information or an algorithm about how to calculate q and r. So I'm not going to cover the proof in this video, and actually I'm not going to cover any of the proofs in this video. What we're going to do when we want to find q and r, we're going to use synthetic division, which I will show you now. We're going to use the example to find all the zeros p of x, where p of x is equal to x cubed minus 3x squared plus x minus 3. And we do have to guess at the first root. So you can graph this maybe in a graphing calculator to find the first root, or you can remember from middle school algebra, the first thing you would do is you'd look at the coefficient in front of your highest degree term. So here, our coefficient is 1, and 1 factors into 1 times 1. And then our factors here for our constant, which is like minus 1, 1, 3, minus 3. Whatever the factors are here, then your first root can be any factor from here times a factor from the constant here. We're going to choose 3, and we'll verify it's a root. You can plug it in. So we have 3 cubed, which is 27. And then here we're going to have 3 times 9, which is minus 27. Then we have plus 3 minus 3 equals 0. So we verified that 3 is our first real root. And then we're going to use synthetic division to get the rest of the remaining quadratic. So in other words, we have x equals 3, then we take these coefficients. We have 1, minus 3, 1, and minus 3. The first thing we do is we bring down our first number, which is 1. Then we're going to do 3 times 1 is equal to 3. We're going to add these two numbers. Minus 3 plus 3 gives us 0. And then next we're going to do 3 times 0 is equal to 0. Now we're going to add these two. 1 plus 0 is 1. Now we'll do 3 times 1 is equal to 3. And minus 3 plus 3 is equal to 0. So these are our numbers here, 1, 0, 1, 0. This last 0 here is good because it does indicate, it's our second check, that x equals 3 is a factor. But we had already verified that, but this is kind of further proof. If you didn't get a 0, you should check, you need to find a different first real root. But now we can say that p of x is equal to x cubed minus 3x squared plus x minus 3 is equal to x minus 3, that's our first real root. And now we have 1 times x squared, 0 times x, 1 times, and then 1 times 1. So this is the quadratic that is left over after we divide this polynomial by x minus 3. From here, once we have a quadratic, that's easy enough to factor because we have x minus 3 times x squared plus 1. Because we're in the field of complex numbers, this x squared plus 1 can be factored to x plus I and x minus I. So this is our factorization. Next, we have the definition of a 0 of a polynomial. A number a in f is called a 0 of a polynomial p in p of f if p of a is equal to 0. This is totally consistent with the definition you're used to from middle school. We have the definition of a factor of a polynomial. A polynomial s in p of f is called a factor of p in p of f if there exists a polynomial q in p of f such that p is equal to s times q. From our last example, p of x equals x cubed minus 3x squared plus x minus 3, we found several factors. First, we have x minus 3 as a factor, our x squared plus 1 is a factor, and what else? Well, this is the same as x squared plus 1, but then we also have x plus I as a factor and x minus I as a factor. We have this theorem that says each 0 of a polynomial corresponds to a degree 1 factor. So putting these two ideas together, suppose that we have a polynomial in Pf and a is a scalar, then p of a equals 0 if and only if there is a polynomial q in p of f such that p of z is equal to z minus a times q of z. From our last example, we had x equals 3 was a 0 because when we plugged in 3 we got a 0, and also we can factor p of z into z minus a, z minus our 0, times another polynomial. We have our next theorem, a polynomial has at most as many zeros as its degree. This is something, again, you know from middle school. So suppose p of f is a polynomial with degree m greater than or equal to 0, then p has at most m distinct zeros in f. And I guess really I should stop saying it's what you know from middle school, because the difference is now you're talking about polynomials over possibly complex numbers, not just real numbers. So it's a little different. Not everything generalizes like that. So this is important. You know that this theorem is the same as middle school. And our last example where we found all of the zeros of p of x equals x cubed minus 3x squared plus x minus 3, you notice the degree of our polynomial is 3. So according to this theorem, we should have at most 3 zeros. And that's exactly how many we found. We have x equals 3 as a 0, x equals minus I, and x equals I are all zeros. Now we are ready to go over factorization of polynomials over C. So the fundamental theorem of algebra says that every non-constant polynomial with complex coefficients has a 0. You may be trying to picture this, and you may picture this counter, or what seems to be a counter example, this quadratic, something like maybe y equals x squared plus some constant, let's just say 2. Clearly, there's no 0 here, so what's up with this? And certainly, if we stayed in the real numbers, you would be absolutely correct. There's no 0 here. However, for complex numbers, x can be equal to plus or minus 2i, right? As for graphing it is a little more difficult because when you graph complex functions, you need two axes because basically each complex number, remember a complex number is equal to a plus bi, each complex number requires an entire axis to graph. In other words, if I want to graph z equals a plus bi, I'm going to have a real axis and an imaginary axis, and then I graph a over here, b over here, and this is my 1 point, a plus bi. It can't be graphed on a singular axis. For that reason, if you talk about functions of complex numbers, you're going to have a domain as a plane and the range as a plane, and you talk about mapping from the domain to the range. But that's more than I meant to get into. Just to say that the fundamental theorem of algebra, now that we're talking about polynomials over the complex field, every non-constant polynomial with complex coefficients has a 0. We have this next theorem of factorization of a polynomial over C if a polynomial P is in the space of polynomials over the complex numbers, and it's a non-constant polynomial. Then P has a unique factorization except for the order of factors of the form P of Z is equal to a possible constant C times Z minus Z1, that's the first 0, Z minus Z2, the second 0, up to Z minus Zm, where Z1, Z2, up to Zm are complex scalars. The proof is interesting because it is inductive. It's induction over the degree of the polynomial, and it's in your book, and I am not going to spend time doing it here in this video. But as we had seen in our previous example, we did this factorization using synthetic division, and the solution we got was P of x is equal to x minus 3, x plus I, x minus I. So it's exactly this form here, and this is an example of this theorem. Next, we're going to talk about factorization of polynomials over the real field. Next, we're ready to discuss factorizations of polynomials over the real numbers. So we have real coefficients. A polynomial with real coefficients may have no real zeros. We had discussed this example earlier where we have a quadratic plus some constant. Clearly, there's no zeros here. Next, we have this theorem, polynomials with real coefficients have zeros in pairs. So suppose P is a polynomial over the space of polynomials over C with real coefficients. Now, if Z1 is a complex number and is a 0 of P, then so is its complex conjugate. In other words, if Z1 is a 0, then so is Z1's complex conjugate. And again, bringing up our previous example, P of x equals x cubed minus 3x squared plus x minus 3. It factors into x minus 3, x plus I, x minus I. Here, our one root, x, which is I, is a complex number, so its complex conjugate, negative I, is also a root or a 0 of the polynomial. So this is an example of this theorem. Taking a closer look at this x squared plus 1, we can use the quadratic formula from middle school algebra, and we see that we also get the plus and minus I as our roots. We're going to be taking a closer look or using this quadratic formula a little more in our next couple of examples and theorems. We have this next theorem, factorization of a quadratic, our x squared plus bx plus c. Suppose b and c are real numbers. Then there's a polynomial factorization of the x squared plus bx plus c equal to x minus x1, x minus x2, where x1 and x2 are real numbers. This is key. If and only if b squared is greater than or equal to 4c. Again, looking at our last example, px equals x cubed minus x squared plus x minus 3, at some point we get this x squared plus 0x plus 1, where b is equal to 0, c is equal to 1, and also a is equal to 1, here you can see that b squared is less than 4c, which means there's no factorization of the form x minus x1, x minus x2, where x1 and x2 are real. There's only a factorization where we have complex numbers. And again, that's because if we look at our quadratic equation, our real root x, let's say x1, is equal to b plus or minus the square root of b squared minus 4ac all over 2a. And when this b squared is less than 4ac, what we get in our square root is a complex number. And therefore, this condition here, the b squared is greater than or equal to 4c, is what's necessary to get a factorization with x1 and x2 being real numbers. We have our factorization over a polynomial theorem. Suppose p is in the space of polynomials over real numbers. It's a non-constant polynomial. Then p has a unique factorization except for the order of factors of the form p is equal to a constant times x minus x1, the first root, the first real root, x minus x2, the second real root, up to possibly m real roots, and then the factors x squared plus b1x plus c, which cannot be factored to real roots because this is where our b squared is less than 4c. Another factor that possibly cannot be factored to real roots, x squared plus b2x plus c, up to x squared plus bmx plus c. So I'm going to rewrite this factorization again. C, which is a real number, a constant. Our terms here, our factors here, these are all where we have real zeros, x1, x2 up to xm. These quadratic factors, x squared plus b1 plus c1, all of these are complex zeros that come in pairs, z and z bar, because in these terms, these factors, our b squared is less than 4c. And using the same example, px equals x cubed minus 3x squared plus x minus x, that factors into x minus 3. This is where our real root comes in, plus a quadratic term where b squared is less than 4c, and that's where our complex roots come in. So this is kind of an example of what this form looks like. And that's it for our review of complex numbers and factoring complex polynomials. To review what we have covered, we talked about complex numbers. Z is equal to a plus ib when a and b are real numbers. A is called the real part, and the b that gets multiplied by I is called the imaginary part. We define the complex conjugate, which we denote with z bar, is equal to the real part of z minus the imaginary part of z times I. We also define the absolute value, which we denote with the absolute value symbol, z, is equal to the square root of the real part of z squared plus the imaginary part of z squared. We discussed many properties of complex numbers as well. The next thing we did is we reviewed polynomials. We defined a polynomial over a field f as a function p of z such that a naught plus a1z plus a2z squared plus amz to the m, where a naught, a1, am comes from the field f, that this statement is true for any z also in the field f. Next, we looked at factorizations of polynomials over C, complex numbers for coefficients and also complex variables. So we had the first fundamental theorem of algebra. Every non-constant polynomial with complex coefficients has a zero. We defined how to factor polynomials over C, and we used the synthetic division and this example in the main part of our video. We then talked about factorizations of polynomials over R with real coefficients. So a polynomial with real coefficients may have no real zeros, and this is key. We're talking about real zeros in this case. We have the theorem that polynomials with real coefficients have zeros in pairs. In this case, they're possibly complex. So suppose P is a polynomial over the space of polynomials over C with real coefficients. If Z1 is a complex number and is a zero of P, then so is its complex conjugate. That is, Z1 complex conjugate is also a zero of P. We had this theorem of factorization of a quadratic. Suppose B and C are real numbers, then there is a polynomial factorization of x squared plus bx plus c if and only if b squared is greater than or equal to 4c. We have this theorem of factorization of a polynomial over R. Suppose P is a polynomial over the space of polynomials, and it's a non-constant polynomial. Then P has a unique factorization except for order of factors of the form C, x minus x1, x minus x2 up to x minus xm. These represent the real roots of the polynomial, times x squared plus b1x plus c1, x squared plus b2x plus c2, x squared bmx plus cmx. These quadratics then represent the complex roots. And that's it for this video. Thank you for watching.